Lab is always pretty much a duplicate. 2 days. Okay, we got it going. Pittsburgh Compound B PET imaging, showing some Alzheimer's over here with different colors. That compound can be found on Wikipedia, and this colored version, if you want. The one you have is black and white. Here's another example of why is this compound useful for PET imaging? Because it has a carbon-11 isotope, the methyl group, the carbon with 4 bonds, 3 to H's, 1 to nitrogen. Okay, this carbon is carbon-11, man-made, and then the compound itself has to be made. It's organic chemistry. Good-looking compound, right? Every standard bonding. What's standard bonding for nitrogen?
3 bonds, 1 lone pair.
Okay, 3 bonds, and then there's a lone pair there. Standard bonding for oxygen.
2 bonds, 2 lone pairs.
2 bonds, 2 lone pairs. So you got to know where lone pairs are at. That's a standard sulfur, just like a standard oxygen. Sometimes this bond is not shown. Sometimes you might want to show a dash between the O and the H, but a lot of times it's sort of condensed down. That's supposed to be a little bond there to show bond to carbon. Here's another example of using carbon-11 for PET imaging. This is a prostate, okay, and showing prostate cancer. Okay, that uses this compound here. But what's the name of this compound? You know from Gen Chem. Got your Gen Chem book? You need to routinely review your Gen Chem material, right? Everybody got a Gen Chem book, right? Do what?
Acetic acid.
It's the anion of acetic acid called what?
Acetate.
Acetate. Everybody got a Gen Chem book. Okay, important stuff in there. Polyatomic ions, calculations, molarity, yield calculations. Many things from Gen Chem will be used. You need to be reviewing your Gen Chem material from your Gen Chem book. Have that handy. Everybody got your organic book today? Okay, can we look at it? Is it raining? Gotta have your textbook, okay? I brought mine from when I was an undergraduate. All right, right here, with Wade, and my solutions manual. Okay, here we go. It's falling apart a little bit. There you go. Mine cost $67, brand new. Okay, and there's my solutions manual. Still got it. Good stuff. Got to make good use of your textbook. So, in this compound, the carbon here, see this is a carbon. You see that CH3 here?
Yeah.
Carbon with 3 H's? Sometimes you may draw it in. I mean, sometimes it may be shown like that. But this carbon, what they used here was acetate, but the carbon, the methyl coming off is carbon-11. Okay. Simple carbon-11 acetate used for that imaging. Okay? Isotopes are very important. Isotopes of carbon, we also look at the isotopes of hydrogen, which have names, deuterium, okay, and then tritium radioactive. So more applications. Okay, let's see where we left off at, green sheet. I see we did not do one yesterday. D, HCN. I already gave you the answer, it has 2 triple bonds. HCN, how many DUS? I was actually on the DUS page. What does nitrogen do to the formula? Subtracts an H. So that's like there's no H's here. 1 carbon, what's max hydrogen?
4.
2n plus 2n is 1, 4. 4 is max, you have none. How many DUS? 2. So I can see 2 DUS. I know I'm going to have 2 double bonds, or 2 pi bonds, 1 triple bond. This compound's going to end up with a triple bond. Because you only got 2 atoms, you can't make a double bond to hydrogen. Okay? But let's do it systematically. systematically. Let's bond the carbon and nitrogen. How many valence electrons are we dealing with? 10, right? Am I right? 5, 4, 1? Okay, let's have 10. Where do you want to put the H?
Carbon.
I'd recommend carbon. Now, we can't put any more bonds. Systematic. I don't want to make any double bonds yet. My systematic approach is to do this, then lone pairs. Single bond, then lone pairs. Where do you want to put lone pairs first?
Nitrogen.
Nitrogen, how many lone pairs? 3. Now nitrogen has an octet. Now has 8 electrons around it. How many we got on the board? 2, 4, 6, 8, 10. That's it. No more electrons to put up there. Is this a good structure? Is carbon happy? Octet?
No.
No octet. We need to have all octets. That's sort of rule number 1. So this is not a good structure. Well, what's the charge of this structure? Or charge of the nitrogen? How many does it own? Owns 7. How many is it supposed to own? So what's the charge? -2 or 2 minus. What's the charge of the carbon?
2 plus.
Okay, 2 plus. All right. It's net neutral. We can tell that from here. This is a neutral compound, because if it wasn't, I should have given a charge with the formula. Okay? It's net neutral. So what can we do from here? How can we make this better? Because nitrogen with these lone pairs needs to start sharing. Okay? These electrons we can move in here. What does this arrow mean to you? The arrows like this need to mean something to you. Okay? What does arrow mean?
Forming a bond.
Right, you got to know what that means. Moving in here and making a bond. Resonance arrow. We now have double bond between nitrogen and 2 lone pairs left. Are we done now? Nitrogen has an octet. But what about carbon? No octet. What's charge of the carbon here?
1 plus.
Just plus charge of the nitrogen?
Minus.
Yeah. Okay, what do you want to do next?
Make another bond.
Ask the nitrogen to share again. These electrons move in here. What does that arrow mean?
Make the bond.
Now we have H, C. Now we have triple bond and 1 lone pair left. Octet, 2, 4, 6, 8. Octet, 2, 4, 6, 8. Now we're good. Charge.
Neutral.
Neutral. It's a standard nitrogen now. 3 bonds, 1 lone pair. Standard carbon, 4 bonds. Here's your good structure. Everything has octets. Everything's actually also neutral. Okay? You could do a structure with the hydrogen on nitrogen. But I'm not going to do that. That would be a constitutional isomer. This is the most common structure. When you say ACN, it's usually referring to this structure, this compound. Okay, systematic approach. Functional groups, we looked at them. We'll look at that C78602 this afternoon. It's pretty much time to look at hybridization. Any questions though? And we saw we ended up with 2 DUS, like the formula said we were going to have. Triple bond. Okay, hybridization. I gave you today acid-base handout. Very important. Tomorrow's lab will include some acid-base chemistry. Functional groups, any questions about those? Okay, let's look at hybridization. Methane, CH4. You know, we drew this on the board, or you can draw this just like this, 4 bonds to hydrogen. We need to look closer at these. What type of bonds are being made? Geometry of the bonds, bond strengths, bond lengths, things like that. Okay? Let's look at ground state configuration again. Valence. We've got 2s for carbon, and then 2p. I'm going to draw this higher up here. 2s is here, and then we have 2p. We have valence shell of carbon, 4 valence electrons. Look at the problem here. Methane is known to have 4 equivalent CH bonds. You can determine that a variety of ways. For example, X-ray crystallography. Okay? That's known. Experimentally known. 4 equivalent CH bonds. How do you make 4 equivalent bonds with this type of orbital setup? For example, this looks like a lone pair. 2 electrons on carbon. This, we could bring in an electron and make a bond with this orbital and that orbital, and then what do you do with this? The other thing is, you got 4 orbitals here for carbon to make maybe 4 bonds, but if you use those 4 orbitals, the bonds would not be equivalent because we're using an S and then 3 Ps. How are you going to get 4 equivalent bonds using that setup? You can't. You don't. That's ground state. I don't know what the purpose of ground state is other than to give you something to engineer. There's probably something there, but we need to go to a hybridized state. Carbon bond, things bond in hybridized states. Okay. Let's set this up right. I wish I'd drawn this over here, because I want to go sort of that way. I'll come this way. We're going to hybridize. And hybridize is just a fancy word for what? Mix, combine. Okay? We're going to mix all 4 of these up, these orbitals, and we're going to get 4 equivalent orbitals. And we're, boom, 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 boom. Mixing the orbitals. This is largely based on math. Okay? We got to get to this. We got to get to 4 equivalent orbitals. How does it do it? Well, chemists, mathematicians study the electron structure. Okay, and there's certain math that leads to this. That's beyond what we're going to get into. Here's the way I'm going to describe it. You ever mix chocolate and vanilla ice cream? No? Let's mix 3 scoops of chocolate and 1 scoop of vanilla. Put it in the blender, blend it up, and now let's scoop out 4 equivalent scoops of ice cream. It's going to be blended. That's what we did. 4 equivalent orbitals. All right? And we're going to call these, we got to give them a name. They're no longer S's, they're no longer P's. Okay? We mixed all of these. Okay? You can say all are mixed. Well, we named these according to what went into the blender. What went into the blender? 1s and 3 p's. So we're going to call these sp3s. Okay? 4 equivalent sp3 orbitals. This is energy. Right? Energy. Isn't S lower energy than P? Ground state. What's going to be energy of these new orbitals that we form by just mixing in the blender? The energy is going to fall in between these. Right? Closer though to which ones?
P.
Why closer to P?
There's 3 of them.
Because 75% of the mix is P. If you mix 3 scoops of chocolate and 1 scoop of vanilla, your mix is going to be more like chocolate. But not entirely chocolate because you got a little bit of vanilla in there. So that's simplistically, that's where the energy sits. It's in between, but closer to the P. What do these orbitals look like? We know that these are spherical, right? We drew them yesterday in dumbbell. What do these look like? Well, I'm not going to try to mix all 4. Let's just mix 2. We mix let's mix an S and a P. 1 S and 1 P. Now the S has a certain phase, and the P orbital has a certain phase, all right? And it's opposite of each lobe. And if you mix these, what you end up getting is, here's the nucleus in the middle here, plus all here, plus here. This plus on plus reinforces each other. Okay? And you get a good reinforced orbital. And it sort of looks like in between. Not as elongated, not as round, but maybe something like touch elongated but more rounded. Okay? This is not precise. This is crude drawing, okay? The general idea. On this side. What happens on this side though? The phases of the 2 orbitals are canceling each other. And like 2 waves coming together and canceling. Okay? So on this side, you get something that's actually canceled. And it becomes like that. Not completely canceled. Alright? And so I'm trying to show you an sp orbital where we combine 1s and 1p. With the shape looking sort of in between an S and a P. There's pictures here, crude pictures again that I've drawn to clarify this point. This is called the back lobe. When we start drawing these hybrid orbitals, we will not draw the back lobe. It just gets too cumbersome, too crowded to draw it. And we will never refer to the back lobe, but it's there. Near the end of the course, we may mention back lobe. It's important at one point. All right. So let's put these now around the carbon. How are they oriented around the carbon? Four hybrid orbitals. What's the best way for hybrid orbitals to be spread out? What's the best way for anything to be spread out? Four things. If I brought four balloons together and tied them together at the little tie part, how would the four balloons spread out? They would spread out in a tetrahedral manner. That's nature. These orbitals spread out in a tetrahedral manner around the carbon. How do you draw a tetrahedral? Two in the plane, one forward, one back. Okay? Carbon, two in the plane. That is, on the board here, we can draw one straight up, And then here, what are the bond angles between in a tetrahedron?
109.5.
109.5, that's why I'm drawing this about 109.5. If I drew this like that would be 90. So it's a little bit greater than that. Okay, that's 2 in the plane. Then we have one forward. Okay, we draw forward bonds bolded like this. And then one back. And as you go away, it gets smaller, like it's tailing away from you. This one gets bigger as it's like it's coming towards you. Okay? But I'm trying to draw orbitals first. To me, though, it's better, it's easier if I start with these lines and then I can draw in the orbitals. Okay? These are really orbitals. Let's put them here. Boom. Kind of forget about the line. I drew that to help me draw in the orbitals. I'm drawing these 4 now. Okay? Back lobe here. Alright? Don't draw it. It's there. But I ain't going to draw it because it's going to get messy. Alright? Draw it here. Alright? Yeah, that's a little ugly. Alright? This is supposed to be the 4 hybrids around the carbon. Okay? And each one of these is an sp3. Alright? sp3, sp3, sp3. Let's redraw our methane. I'm going to draw it with the actual correct sort of geometry of these bonds. Okay? Now, I first had it, it looked like it was all planar with 90 degrees. You draw it first, how I first had it, your bond angles were 90 degrees. Boom, boom, like an L. That's not right. We often draw it like that, just quickly, but this is more precisely. Okay? So what do we have here? I reckon we can get rid of this. This is bonding to what? An H. Okay? What's going on here with this bond? 1 electron from each interacting to make a magical bond. 2 electrons shared covalent bond. But what's interacting? It's really the electrons in orbitals. The orbitals are interacting to make that 2 electron covalent bond. What type of orbitals are interacting here to make this bond? It's an sp3 orbital from the carbon, and then what type of orbital from the hydrogen? All it has is an S. And the S, there's no hybridization, there's nothing to mix it with. And what's the shape of an S? Spherical. And so this is sort of the H here, spherical, we can call it the H, and it's 1S. That's your sp3. It's the second shell that we're hybridizing. Usually you don't see a 2 written there, but if you're going to do a 1, you're like, well, why did you put a 2 here? The s orbital and and then you got 2 electrons here. Showing the electron from H, the electron from carbon that sits here. Okay. Let me do this instead. I think we drew X's yesterday. Let's make the electron from the H an X. And there's your magic to make that bond that we're showing here simplistically. What type of orbitals are overlapping to make a bond? Important question. sp3 and the S, okay? What do we have up here? We have 1 electron from carbon and then 1 from hydrogen. Okay? I'm just sort of showing it that way, the hybrid here, okay? Many of these ways have limitations, they're not complete, okay? It's like, well, where's the S orbital? I'm not showing it, I'm bringing the X in, okay? Here you can see a better view of it. Okay, what's going on here? 4, okay? Boom, boom. I'm not going to complete that, it's the same as this. We got 4 identical bonds here, okay? Boom, boom, boom. The arrows are your 4 valence electrons that carbon brought in. And the X's are the electron that the H brought in to each bond. And there is your 4 equivalent bonds. Tetrahedral. Okay, all these are 109.5. But so is this too. It's just more difficult to see because one bond's here, the other one's coming towards you. But that's 109.5. Okay? You do need to have models. Very helpful. We can make a tetrahedral. Okay, we'll do it here. There's your tetrahedral. One straight up on the board. One that way on the board. These are all H's out here. Right? This one's coming towards you. Right? This is the board here. Off the board towards you. This one's coming off the board back. Okay? Alright? Now, this one is right in front of the back one. Now up here, I didn't draw this one right in front of that one because then you wouldn't be able to see it if I drew it that way. So it's sort of drawn on the board more like a little bit like that. Alright? But you have one of these in your hand, you look at your drawing, you say, you see the nuances that are here. Alright? So, this is a carbon that's tetrahedral. The important thing here is, so if this is the starting point, the fourth thing here is we have 4 electron regions. This would be the answer to the question. 4 regions. 4 regions requires, we need 4 hybrids. 4 hybrids. Since we needed 4 hybrids, we put all 4 original in the blender. It gave us 4 hybrids. 4 hybrids allows for 4 regions. It all leads to the same thing, tetrahedral, 109.5. We can compare this to the next example. Questions while I'm erasing and stuff?
The electron that the hydrogen donates to the bond isn't hybridized, right?
This orbital is not hybridized. This is overly simplistic. You go to a higher level course, you're going to talk about molecular orbitals. Once these start combining, it really becomes a new orbital. We're not going to talk about that ever in this course. We're sticking with these atomic orbitals is simply combining. That's it. Right? You can build on that as you go forward. Let's understand this type of theory and approach first. Importantly, what we left out here, this is a sigma bond. It'll be better defined next time. That's a sigma bond there. Usually you don't talk too much about the H. We'll look at this when we have carbon-carbon bonds. Okay? So I think we can do that a little bit better or on the next example or two. Okay, let's green sheets. Make sure we're covering our different points. Sigma bonds rotate. Graph the electron configuration right here. Here's the electron configuration for this hybridized setup for that carbon. Okay? We'll be doing more examples. Sigma bonds can rotate. I reckon we can say that here because this can rotate. Okay? See how that's spinning? If this is an H here, all right, it can spin. A sigma bond is a head-to-head overlap of orbitals. head-to-head overlap. Again, we'll show this. Let's bond these two. How could we bond them? Head-to-head. It looks like this, the two heads, but end-to-end, okay? Bam, I just made a signal bond. Okay? And look, it can rotate. Now you hear a little bond string there, but see it rotating? It's still connected. All right, a signal bond. How else could we have bonded this? Another way would be side to side. Boom. I just glued them together, bonded them together. Well, that can't rotate. Because if you try to rotate this, I just broke the bond because it's no longer full side to side. I mean, if you're just going to do point to point, then you maybe can rotate, but that's, no. So that's the difference. Signal bonds can rotate. Next example, ethane, ethylene. Ethylene, let's see. Okay, let's focus in on this carbon, this one. The discussion is the exact same for the other one. To have a carbon-carbon double bond, you got to have two carbons. You can't have just one. All right? Let's focus on this carbon. How many regions around this carbon? Electron regions. First question we typically want to ask. Three. Single bond, double bond. 3 regions. Because it's 3 regions, how many hybrids do we need? 3. Okay? We only need 3. The 3 regions are going to be spread out what way? What's the best way to spread 3 regions out? Trigonoplanar. Trigonoplanar comes from 3. 3 hybrids. Your hybrid set your geometry. We need 3 hybrids. How do you get 3? Well, you only put 3 in the blender. Because however many you put in the blender, that's how many you get now. So instead, all right, you may not be able to do this every time easily. I'm just going to blend this one in 2 of those. Put 3 in the blender. And I'm going to pull out three. And we're going to put these here. Boom, boom, and boom. And we're going to call these sp2s. Okay? 3 equivalent sp2 orbitals. Importantly though, what did not go in the blender that was there? We didn't put 1 p orbital in the blender. It's still there. Okay? Still there. A p orbital is still there in this case. We didn't hybridize it. Now, I'm not keeping track of the relative energies. These are 3 hybrids now. I'm not going to draw them. We'll look at them relatively. Let me ask you this question. Are these higher in energy or lower in energy than the sp3s that we erased? Why lower?
Because there's less P than the other one.
Less P than the other one. Another way you can look at this is how much S character is here? 1 out of 3 is the S. 33% S. So, what's the percent S for the sp3s? 25% S. More S character means these are lower energy or higher energy? Lower energy. More like S. What about shape? Very good. More rounded because they're more S-like. What about length of the orbital? Very good. More S character, more rounded and shorter. More P character, longer and, okay? Yes, that's exactly how you look at this. Relative. Now when I draw these hybrids, they're going to look just like the sp3s because I can't really differentiate them. All right? These three, around the carbon. Now trigonoplanar is easy, nothing forward or back, everything's planar. All right? You got one here, you got one here, and you got one here. Roughly trigonal planar. And what's bond angles here? 120. 120, 120, for a total of 360. All in the plane. Okay, but let's put the orbitals here. 3 hybrids. All right? Here. Here. Not drawing back lobes. This probably looks just like the sp3, but now they're sp2s. We know that they're actually shorter than the sp3s. Okay. There you go. Range in trigonal planar, because that's nature. They want to be these electrons, ultimately electrons, are going to be spread out here. What are these two interacting with? Yeah, it's the H. Okay? sp2 and then the 1s. Electrons here, I'm not going to get all the fine details. We already did that once. Okay, 2 electrons making the bond. And the same thing here, right? What's this interacting with? You got another carbon over here. And this carbon is the exact same hybridization setup. And I can draw this, boom, boom, and boom. And what's coming this way? The sp2 of that carbon. And so what's going on right here? One electron in this orbital, one electron in this orbital, overlapping to make a bond. What type of bond is this? No, these 2 orbitals are like this. That's head to head. Okay? Sigma bond. This is where you can really see it. Orbital here, boom. Head to head. Sigma bond. Your hybrids make sigma bonds. We can finish this up and put the okay. What else is on this carbon? Here we made three sigma bonds here. That's a head-to-head. A volleyball kind of doesn't have a head, I reckon. But that's why I was reluctant to do that. Here it's, okay, these are head-to-heads. But that's also a sigma bond. It's easier to see here, I think. What do we have here? We have sigma bond to H, and sigma bond to carbon. Here instead of X's, I'm going to do HH and carbon to distinguish. What else do we have on this carbon? P orbital, okay? How is it positioned? It's positioned orthogonal or perpendicular to this plane. All this is on the board. The P orbital is coming out like this and half back. Okay? Called orthogonal or perpendicular. I can't draw it like that. I'm going to have to draw it straight up. If I draw it straight up, you have to envision that this stuff is like this. Now we can draw the P orbital straight up. Okay? What's a P orbital look like? Well, it's a P orbital. Kind of like that, but I'm going to draw it longer to distinguish, because we know the P orbital should be longer than this hybrid, because this has some S characters, right? Exact same carbon over here. And one of the carbon electrons sits here. The 4 arrows are your 4 valence electrons. Okay? So we got 1 electron here. This carbon also has an electron there. Okay, I reckon we'll call it X. But these orbitals are interacting. How do they interact? Side to side. Up and down. That's one bond here. Okay? I'm just showing it, it's interacting above this bond and below. Okay? What type of bond did we just make there? Pi bond. Side to side overlap. So the hybrid system, we can call it, the original, the hybrid system is like this if we want to consider. Then you got the 2 p orbitals here, sticking straight up, and they're interacting side to side. It looks like they're a long way away, right? How are they interacting? Well, that's causing my drawing if they ended up being a little bit longer away. They are close enough to bond, but it's actually a weaker bond. Sigma bonds are stronger. Maybe it's weaker because there is some sort of distance here between the 2. Yeah? This is what we have here. And so we have a sigma bond to carbon. We can clarify this to carbon. Pi bond to carbon between the 2 carbons. Sigma bond here using a hybrid. And then pi bond using the P. Pi bonds are made using P. Sigmas are typically made using hybrids. Altogether, what is this? 2 bonds, or a double bond. Whenever you see a double bond, what do you see? You should see a sigma and a pi. So that's why yesterday I was saying, DUS, it has a double bond. Pi bond. I see 1 pi bond. Right? Sigma and a pi. Okay, let's continue on. There's things you probably could say here, but we'll eventually say them as we summarize, etc. Let's look at the next example. Oh, by the way, because of this pi bond, these 2 carbons cannot rotate. Here we go. Here is a pi bonded carbon. I wish I had larger models for double bonds and triple bonds. These models just show sort of like this, double bond there, okay? Head to head there, and then you got 2 orbitals that are interacting like this to make that double bond, which is just shown as 2 lines. But this cannot rotate. And your models are built to show that, to have that limitation. You cannot rotate this, you're going to just break it. Because that pi bond, if you try to rotate it, you're breaking it. It's got to remain full to full, side to side overlap. Right? You're breaking it. It ain't going to want to be broken. There's some type of high energy processes where you can, but essentially the bond gets broken, then it allows it to rotate. On the other hand, if you have something that's sigma bonded, this is all just single bonds. Look at this. See, that can all these can rotate. You see? And it's still bonded. And eventually we'll have to look at this. How does this thing like to exist? It can do all this free rotation because it's sigma bond. You put a pi bond in here, it's going to, I can't rotate anymore. I'm stuck right here. That can't rotate, but maybe this still can. But down here it can't. Next, ethyne. Ine. What does the ine ending mean to you?
Triple bond.
Carbon-carbon triple bond. So you got to have 2 carbons. Nomenclature. Tomorrow I'll give you or actually I may send it by email. Okay. Nomenclature for test 1 on alkanes is covered by video only. There's a handout that goes with that. Okay? And we'll learn prefixes. Meth, eth. Eth is 2 carbons. Ethine, 2 carbon alkyne. There you go, ethine. Let's look at it. We're going to see sp hybridization. Let's start here. How many regions around this carbon? 2. Right, 2 electron regions. How many hybrids do we need for this carbon? 2. Your hybrids set your geometry. How many do we need to put in the blender? 2. Y'all just keep saying 2 for every question and you'll be right. Okay? 2. Which ones do you want to put in there? This one always goes in. This one and... Okay, don't say 2 here. And how many P's?
1.
1. Okay. Just this. What are we going to get? You put 2 in the blender, how many do you get out? 2. If we put 8 in the blender, how many are we going to get out? That's more important. We're getting 2 when you deal with 6 and 8. Okay, aromatics, molecular orbitals. Okay. 2. We're going to have 2. What do you want to call these? How about we just call them SPs? Because this comes from what went in. Mixing an S and a P, we're going to call them out and call them SPs. What percent S are these? 50% S. Okay. These orbitals are thus even more rounded and even shorter. More S character, more like an S. The energy is going to sit really right between these two. Right in between. Okay, what's left over? 2 P's. 2 P's left over. How are your 2 hybrids going to be spread out? If I tied 2 balloons together, they would spread out linearly. If you tie 2 balloons together and one is up and the other is like this, I want to see it. The other one's going to go this way. We got a carbon, 2 hybrids around it. Okay? There's 1, there's 2. I didn't do the back lobe here or there for that one. That guy. What is this one interacting with? H. Right? 1 electron from carbon, 1 electron from H interacting. That's a 1s, and this is a what? An sp. That's an sp. What is this one interacting with? We got an identical carbon over here. This carbon over here also has 2 hybrids. sp and sp. That one on the ends interacting with an H, 1s, 2 electrons. But what do we have right here? 1 electron from the carbon we're dealing with, and then the other one we'll call X. 1 electron from each. Really, you got 2 orbitals interacting. What 2 orbitals are interacting? sp and sp. What type of bond is made here?
Sigma.
That's a sigma bond. Head-to-head overlap of the 2 hybrids. What did we just make? We made sigma bond to hydrogen and sigma bond to carbon using the 2 hybrids. What else is left over on this carbon? P orbital. Okay? All this is in the plane here. Nothing forward or back yet. We're all good here. Flat on the board. This carbon's the exact same. There's 1 electron here. There's 1 electron there. These orbitals are interacting to make pi bond. What else is on this carbon?
Another P.
Another p orbital. The other p orbital is perpendicular to that one. And everything here. The other p orbital is coming out like this. And the same with that one. And you have these two p orbitals interacting this way. Another pi bond. How are we going to be able to draw this? I'm just going to have to sort of put it up here, sort of like this. And we're going to have to really refer to pictures better. Okay. The original was, well, I drew the original, yeah. This one you sort of have to go from sort of like tip to tip here to sort of illustrate it. Basically have two pi bonds, and we can show that here. This is being the one carbon, pi bond to the other carbon, pi bond to the other carbon. All together now, what do we have here? Triple bond. And when you look at a triple bond, what do you see? One sigma, and how many pi's? Two pi's. Okay? Two pi bonds. That's why that's two DUS. Because really, every pi bond is a DUS. That's what it says on the sheet. Two pi bonds. That's why triple bond is two DUS. Okay, let's look at some better drawings maybe in the functional group handout. Tetrahedral, pretty straightforward. Let's look at the one we're on here. SP. This is what we tried to just draw. See that sigma bond in sort of the middle, darkened head-to-head overlap? And then that's two pi bonds, not four, because we have above and below for each one. And then linear, you see the H, C, C. What's the bond angle of the HCC bond angle? Yeah, 180 linear. See that bond angle through there? No, not an angle, it's 180. Linear. That was set by your hybrids. Your hybrids set everything, set your geometry. The orbitals are like just left over, but they supply the second and third bond here. And then up top was, they're trying to show the plane there, and then the p orbitals being perpendicular to the plane. Different books will show it different ways. Okay. On the back here, that's at the top, trying to show crude drawings of the hybrids. Makes sense though, right? SP3 should be longer. Or we can say SP should be shorter. More S character, right? I'm drawing the back lobe with each. So these are in between S and P. Everybody got the idea yet? This is going to be important for bond lengths. Which type of hybrid is going to make the longest bond? The longest orbital. Which type of hybrid will make the strongest bond? SP. Why? The lower energy I like better. It is shorter. Usually shorter bonds are stronger, but it's all kind of the same because shorter is usually lower energy. Why is it lower energy? It's got more S character. And aren't S orbitals lower energy than P's? So the more it has S character, the more it's going to be lower. Okay? So all that explains such a table here. This table comes from another textbook. So we can look at bond lengths and strengths. Ethane. They're doing two carbons here. I just did methane, but it's the same setup. Each carbon is sp3. It's got 4 regions around it. Bond angles, all the bond angles here are 109.5. Length of the carbon-carbon bond, 1.54 angstroms. Let's compare that when we go down. The interatomic distance between the two carbons gets shorter and shorter. Why? Because this here is sp3 to sp3. And the hybrids are the answer to everything here. What type of hybrid is here? What type of sigma bond is here? sp2 to sp2. And this is an sp to sp. Okay, so which should be shorter? sp to sp should be shorter because you got 2 shorter orbitals. Okay, let's make a bond. All right, we just made a long bond. All right, because I use my long orbital. So let me use my short orbital. We got to come closer to bond, right? Long orbital makes longer bond, longer atomic distance, interatomic distance. Short orbital, we got to come closer. Shorter interatomic distance. What?
Is the reason that the length of the CH bond is decreasing because they're more similar in shape to the SP versus the SP3?
You're moving on. What are you looking at?
Sorry, that bond as it gets shorter, is that because it's more similar in shape?
Well, the H doesn't vary. It's the same orbital for the H.
But the SP is more similar in shape to the S than the SP3 is to the S.
I don't know that we need to explain. I'd have to think about it. The important thing is the trend right? It may not be a big difference, but it is getting smaller. Because we're looking at the CH bond. This is an sp3 to S. This is an sp2 to S. This is an sp to S. Should this be shorter? Yes, because this is the same orbital, but that one is getting shorter compared to an sp3. You're asking why is it not much of a difference? I'd have to think, but one of the reasons I think is because it's the other one's constant, it's SSS. I have to think about it though. Or you let me know what you're thinking, but let's. The main thing is the trend right? And it is. This trend is right. What about strength? Usually kcal per mole. Kcal is what I would usually look at. Got to be careful here. They're talking about the entire bonding between the two carbons. This makes you think that maybe they're just talking about the sigma bond. No, entire bonding. It makes sense. Single bond, double bond, triple. But is that double 90? No. Why is that not 180? Because this is not 2 sigma bonds. Right? This is a sigma, and this is a sigma plus pi, right? Pi is weaker. The side-to-side overlap is not as good. Actually, these sigmas are not even the same. Because this sigma is sp3, sp3, where this sigma is sp2, sp2. Which sigma is stronger? Top or bottom? That sigma is actually stronger. It's shorter, so maybe this sigma is 100, where that one's 90. But then the pi is weaker, so maybe it's like 74. Okay, so maybe it's something like this. Then down here you have a sigma plus pi plus pi. And this sigma is even stronger. Maybe this sigma, random numbers, is maybe 110. or something, and then the other two add up, you get 231. Okay? So there's a little bit, it's not just a simple look at it. There's multiple things going on here. Again, though, it does make sense. A triple bond is stronger than a double. A double is stronger than a single. But you gotta know what a double consists of. And what type of sigma bond is there? What type of orbitals are being used? And the percent S character really helps answer lots of these questions. Okay, let's see what's below. There's Prozac homework over there. Rank bonds from longest to shortest, etc. Graph the hybridization. What we were doing in the middle each time was graphing the hybridization. We need to do that. What about atoms other than carbon? All right. I'll let you do this because those are spelled out nicely if you do this homework. Let's look at the syllabus, and there's some drug compounds there. Look at Flavix, right in the middle, this nitrogen. Let's ask all the questions about that nitrogen. What's a hybridization? Graph it. Show what bonds are being made using hybrid orbitals. Not a ground state, but a hybridized state configuration. Okay? What hybridization do you expect of that nitrogen of Flavix? First off, what's there? It's not shown. Lone pair. Hybridization. sp3. Why? First question, how many regions around that nitrogen? 4. 4 is sp3 until we say give you an exception. A very important exception. sp3. Okay? Well, what is the orbital layout for sp3? And we're only doing valence, okay? We're not doing subvalence. Right? sp3 would be what? 4 sp3s? Does sp3 have a p orbital left over? How did we get to sp3? We mixed an s and 3 p's. We mixed everything, nothing left over. Here's your sp3 setup. This is energy. But we're not showing any other orbitals, so there's nothing relative to that. Okay, what type of bonds do you see that nitrogen making? I see a bond to carbon. Is that going to be a sigma or a pi? Sigma. Single bonds are sigmas. Also, if we're using these orbitals, what type of bonds are we making? Sigmas. Hybrids make sigma bonds. What type of orbitals make pi bonds? P orbitals make pi bonds. We don't have any p orbitals. We're not making any pi bonds. If you want to make a pi bond, you need to have a p orbital. What type of bonds do you see made there? I see 3 sigma bonds to carbon. I can show that here. Sigma bond to carbon, sigma bond to carbon, and sigma bond to carbon. With the arrow being valence electrons of nitrogen. What else is on the nitrogen? Lone pair. What orbital is it in? The only one it can be in. That one right there. This is a lone pair. And the 5 arrows are your 5 valence electrons of nitrogen. Made 3 bonds, now it has an octet. There's your valence shell. It's filled with 8 electrons. We just graphed it. Can we show the nitrogen? Well, it's tetrahedral. Okay? This is not shown tetrahedral. We don't always show the tetrahedral nature because it's cumbersome to draw. We typically only show it when it's important to show it. For example, it is important to show it over here. For a certain reason we'll learn later. Okay, let's just draw this here. 2 in the plane, 1 forward, and 1 back. Okay? We call these orbitals, but I'm just going to keep it as just a bond. This is bonding to carbon, that's bonding to carbon, and one of these is bonding to carbon. And what's here? That's just a lone pair. Okay? But it occupies that space. These are orbitals, orbitals, orbitals. This is an orbital too. But it's just a lone pair in that orbital. It's not interacting with anything. But it gets its space, carbon, 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 carbon. You see, in real life, if these two are in the plane, in real life, this one is going forward or back. It's just not shown in this drawing. But it's tetrahedral. Okay? Again, this is 2 orbitals interacting, right? I'm just focused in on showing you that. That lone pair is in an orbital that has its region. Okay? All the bond angles here, 109.5 approximately. We know we can vary from that. Okay? So you need to be able, every atom on the board here, you need to be able to do this, except for maybe sulfur, because when it starts expanding in its octet, dealing with d orbitals, we're not going to do that. And there's some notes along the way that tell you to avoid sulfur, particularly in the workbook. Okay, let's look at Cipro. How about this nitrogen here? Oh, before we do that one, let's do an oxygen. How about this oxygen here? What hybridization do you expect? And why don't we do this? Why don't we take a short 1-2 minute break? And while you're doing it, graph the hybridization of that oxygen. Okay? Okay, let's look at the hybridization of this oxygen here. 2 lone pairs, right? How many electron regions around the oxygen? 3. So what hybridization do we need? sp2. sp2 would be how many? And then a p orbital left over. What type of bonds do you see this oxygen making? I see a double bond. A double bond is going to consist of a sigma and a pi. Sigma is used, is made using the hybrids, sigma bond to carbon, and a pi bond to carbon. Right there. Sigma bond to carbon, pi bond to carbon. It's there. What goes in these 2 orbitals? Lone pairs, and we have 6 valence electrons for oxygen. That is what I call graphing the hybridization. I am unique in doing this. I don't think any other professor is going to do this. I don't think any other book will do this. For some reason, books only like to do such when they introduce it, and then they never want to do it again. They never do it for oxygen. I think it's a very good way because it's very systematic. It helps you do it and then assess it. I like to give you very systematic ways to get answers and to understand things. There you go. If we do the geometry, I mean that carbon's down here. Let's do the oxygen first. The oxygen is here. Hybrids are spread out how? Trigonoplanar. Okay? These are really orbitals, right? You want to get rid of the lines. Yeah? This orbital is a lone pair. This orbital is a lone pair. We could have used arrows here. This is coming down, this carbon down here. That carbon is sp2. I mean, it also has an orbital. It's coming up here, and we're making sigma bond to carbon. But it's trigonoplanar. Okay, that's a different atom. Sigma bond to carbon, yeah. What else is on the oxygen that we haven't shown?
Pi bond.
P orbital. It's coming out and back. But that carbon also has a p orbital, right? What's hybridization of carbon? sp2 with the p orbital. It's got one, and these 2 are interacting side to side to make a pi bond that's also there. And so you see that sigma, and then there's a pi bond. This is the graphing of that. All together now, what is that right there? That's your double bond that we see. And the 2 lone pairs, the question could be here, what type of orbital is the lone pairs in?
sp2.
It's sp2. I see it right here. Not a p. The p orbital is being used to make the pi bond. Okay, let's look at this nitrogen here. Graph that one. How many electron regions?
4.
What hybridization do you expect?
sp3.
sp3. Okay, and you would be wrong. This is an exception. Exception. This one is sp2. And there will be many like this. It doesn't have to be nitrogen. It can be chlorine or oxygen. It's sp2. I'll explain why, but let's first just proceed with it being sp2. If it's sp2, what is it going to look like? Well, just like that over there, right? sp2, and then you got the p orbital. What type of bonds do you see it making? There's no trick here. What type of bonds?
Sigma.
Sigma bond to Three different carbons, right? Everybody see that? Sigma bond to carbon, sigma bond to carbon, sigma bond to carbon. What else is on the nitrogen? Lone pair. Since I told you it's sp2, now answer this question. What type of orbital is a lone pair in?
Pi. Or P.
And the only place it can be. Lone pair is in p orbital. And this is the reason it's sp2. But the lone pair wants to be in a p orbital. Why does it want to be in a p orbital here? Because of what's next door. Look at this carbon over here. What's its hybridization? sp2. No, there's no exception here. Does that carbon have a p orbital? Yes. Actually, every carbon in the ring has a p orbital. You look at it, and now we see why it's an aromatic ring, because the definition on the functional group page was every atom in the ring has a p orbital. And it does. You see that hopefully now. Okay? But right here, see, all these are interacting, and that's what makes it aromatic. Can that nitrogen interact in this p orbital game? It can in this configuration. What's going on is this nitrogen has a p orbital, and what are we putting in the p orbital? Lone pair. And that lone pair gets to interact with the neighboring p orbital. Now I drew all 6. All it takes is 1. So I'm going to erase the rest. Right there. And this is very powerful. The lone pair is stabilized by interaction with adjacent p orbital. This can only happen if we put the lone pair in a p orbital. So we do it. If the nitrogen does it, if the molecule does it. This is how it wants to exist. And so it adopts an atypical hybridization. All right? To allow that lone pair to participate in what we're going to later call resonance. Conjugation. Conjugation is when you have p orbitals interacting along the way. All right, what if we stuck with our original? What if we called it sp3? Then this would be trigonal tetrahedral. And it would have been 2 in the plane, one back, and 1 forward. And maybe the lone pair there. That would be tetrahedral, sp3. And if it's like that, the lone pair can't interact. First off, it's not in a p orbital, and it's not lined up correctly anymore. And so in your first answer, sp3, the lone pair can't do any interacting, and that's not as good. Putting this in a p orbital to interact with the next door p orbital, it's a better situation. So that's why it's atypical. Here's a take-home that I will say. Anytime a lone pair is next to a p orbital, the lone pair is going to want to be in a p orbital. We could say other things. As long as it can be. Sometimes there'll be reasons where it can't be, but we'll see other things as they come up. Anytime a lone pair is next to a p orbital, lone pair is like, hey, I want to be in a p orbital. Okay. Let's look at like these nitrogens here. Lone pair. lone pair, lone pair. Important question here would be, which lone pair of the three is in a p orbital? Well, let's do this. Graph the hybridization of the top nitrogen. How many regions around it?
3.
3. What hybridization do you expect? sp2. It is sp2. Any questions? You're thinking, why is it not? It is sp2. We're doing the top nitrogen, sp2. Boom, boom, boom. P orbital left over. What type of bonds do you see the top nitrogen making?
Sigma and
Sigma and pi to one carbon, and then sigma to another carbon. I see a sigma to one carbon, a sigma to another, pi to one carbon, and altogether now that was the double bond, right? We got a double bond and a single bond to carbon. The lone pairs are what type of orbital? The only place it can be. Lone pairs in sp2. How about the lower nitrogen? The lower nitrogen. Hybridization? It's actually sp2. Why? Because anytime a lone pair is next to a p orbital, is this lone pair next to a p orbital? That's a methyl. Okay, what's a methyl? It's a CH3. All right, CH3. Okay. That carbon doesn't have a p orbital. That one doesn't. How about that carbon? Does it have a p orbital? Yes. I mean, there's p orbitals there. There's a pi bond there. P orbital. There's a pi system here. Would this lone pair like to pi bond with that? Yes. This lone pair is going to sit in a p orbital. It's not that big, so it can interact with the other. So the hybridization is what? It's sp2. Boom, boom. What type of bonds do you see that nitrogen making? Sigma bond to carbon, sigma bond to carbon, sigma bond to carbon. And then the lone pair is in a p orbital, participating in resonance or conjugation. Any question about the first one that we did? Because that could, if you take what I said overly literally, this lone pair is next to a p orbital. You might say, well, why is this lone pair not in a p orbital? Why did we put it in a hybrid? That's where the statement needs a little bit more explanation. The p orbital here is already being used to make a pi bond. Down here, there was no p orbital making a pi bond. Could we have two p orbitals here? No. Because only one, if you got p orbitals lined up, like look at this, okay? What if you had a nitrogen with a lone pair here? It's like, well, I want to line up with these p orbitals, and so it takes on a lone pair and you get all this conjugation here. If that's already double bonded, and you got a lone pair, that's already all lined up. Putting this in a p orbital is not going to help you because a new p orbital would be like this. And it ain't lined up with the other 5. So that's kind of what's going on here. The only time you really get this exception for us is when it looks like it's sp3, but it turns out it's sp2. This is plain old sp2. And it's not going to do anything strange to go sp. All right, you got to work on recognizing this, okay? You say, well, what about here tomorrow? And I say, well, and then you, oh, okay, I get it now. So it comes from you doing work and then seeing the examples and getting it in your mind. I can't just sit here and tell you every little nuance. You have to do the practice. You have to recognize it, and you have to ask questions. Okay, that's hybridization, including some the heteroatoms. I focus a little bit on nitrogen because that's important for acid-base chemistry. The same general idea applies to any type of atom. Oxygen, sulfur. All right, how we doing? Green sheet, let's see where we're at. Other hybridization examples. Let's look at carbocations. Let's look at CH3 plus. It is random, yeah? All right. If I just put CH3 on the board, it looks like formula. Right? Charge has to be given with formula. So I need to show the pluses. Now I could also do a CH3 minus. Me telling you it's minus, we're going to have to understand what else is there, etc. Okay, let's do a structure here. You know, I could just draw all three H's around the carbon. Does this have a lone pair? Lone pair? No, because if it had a lone pair, it wouldn't be positive. There's no lone pair. There's nothing here. What's the charge of this carbon? It owns how many? 3. It's supposed to have 4. It's missing 1. That's why this is a positive charge. Okay? Here. Carbon with 3 H's, and that's it. It's called a carbocation. Cation being positive. Carbocation. Carbon is positive. Okay? What's the true geometry here? What hybridization do we expect for this carbocation? How many regions? 3. 3? What do we expect? sp2. P orbital left over. What type of bonds do you see? Sigma bond to H, sigma bond to H, and sigma bond to H. What's in the p orbital? P orbital is empty. Are my bond angles correct in my original drawing? What are the bond angles? Right, 120, right, all the way around? And then you got the p orbital coming perpendicular, half out, half back. But it's empty. Does this have an octet? No, it's only got 6 electrons, 2, 4, 6. 2, 4, 6. Would this molecule like more electrons? Yes. And what do we call something that likes electrons? Electrophilic. What do you call someone who likes wine?
Wine and food.
A winophile. What do you call a molecule that likes electrons? An electrophile. Why does it like electrons? It needs electrons. Anybody got any electrons? This is going to be reactive towards something with electrons. Maybe you got a lone pair. You can come in here and react to this and fill this orbital, and you get some chemistry, reactivity. Okay? But the hybridization is here. All the same questions. Okay? What about this guy? The fact that I showed you it's a minus, we got H, H, and H. What else is here? You gotta have a lone pair. What's another reason to know it's got a lone pair? How many valence electrons we got? Carbon is 4, H, 7. 4 and 3 is 7. But it's an anion. That means it's got one more electron. So 8. 8 valence electrons. 2, 4, 6. Well, then what's the other 2? Lone pair, you see? It's all there. But in terms of charge, if we didn't have a lone pair, that carbon would be positive. But I'm telling you it's negative. The only way it's going to be negative is for it to have a lone pair. All roads lead to a lone pair. And it's negative. This is called a carbanion. It's written on the green sheet, yeah? It's a carbon that's an anion. Carbanion. Hybridization for it. How many reasons? What do you expect? It's sp3. Which is boom, 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 boom. Sigma bond to H, sigma bond to H, sigma bond to H, and what? Lone pair. Right? I mean, that lone pair is in an sp3 hybrid. Don't write this, I'm going to do it quick. What if over here was maybe an alkene? Carbon, you see that, right? There's an H there, okay? If this was it, what would be the hybridization of this carbon? It'd be sp2, what? Right, because over here you got pi bond. We see that, right? It's sigma bond, pi bond. This guy's going to be like, well, hold on. Can I play? I want to come out and I want to be in a p orbital. Look at me. I can play too. And we can all line up. Conjugation. And this would have to be sp2. What would happen? We didn't draw the original. If that happened, these H's would move and adopt trigonal planar. To allow for that p orbital to be there. Okay? But the original, there was no p orbital next door. And the lone pair is not going to want to be in a p orbital if it can't interact. Because actually a p orbital is less stable than a hybrid. Putting it into a p orbital is actually a less stable orbital. But that problem is overcome by the overlap between other p orbitals. It actually makes it better. If there's no overlap, it's not going to want to be in a p orbital. But the overlap is very important, magical, resonance, conjugation. Atoms other than carbon we already did. Key exception. We'll mention O2 MO theory at some point, polarity of covalent bonds. This takes us to our other handout. Oh, it's pink, right? Okay, there's what's in this handout, physical properties. Lots of good applications here. Okay. Polarity of covalent bonds. Hydrogen, H2, would be an example of a non-polar covalent bond. All right, 2 electrons here, right? We can show this here, maybe like, however you want to show it, arrows or something. 2 electrons sitting in there. Okay, it's actually 2 orbitals over interacting. Does this become 1 orbital? Again, we don't need to take it that far. Important though, you have electron density here, it's called, 2 electrons. And the electron density is equally distributed between the 2 nuclei, because the hydrogens have the same electronegativity. On the other hand, if you look at HCl, the 2 electrons here, if we consider it covalent, are not equally distributed. They're more like this. The electrons are pulled more towards chlorine. Right? But the chlorine is more electronegative. And you understand why it's more electronegative, right? Why? But why? Why does it have more, why is it more electronegative?
It's closer to being in an octet than the other, and that's it.
Why is it more electronegative? Doesn't it have to do because it has more protons? Protons are positive, and the electrons in the bond are thus more attracted towards all those protons? You learned this in Gen Chem? Why it's electronegative? I'm not sure. I think it's because it's got a lot of protons. And positive protons pull the bonding electrons towards it. Physics? Yeah? All right. This would be a polar. So the electrons are there. Now what does this do? It's more towards physics, okay? Getting it charged. The electrons are more perturbed, and it leaves this end more partial positive and partial negative. Induction, dipole induction. You talk about this in physics? We can move electrons, we can create these temporary dipoles or permanent dipoles. A lot of times it's temporary because we induce it and then it kind of goes back. But here it's in this setup here, it's sort of permanent. Polar. We have polarity all over the place though. The carbonyl is a very polar, very common polarity. And so the oxygen's pulling. We can show this with this sort of dipole arrow. The electron is being pulled this way, leaving positive on this end. Or we can show it like this, partial plus, partial negative. And so the carbonyl is a polar, I want to say functional group, but we know it's not. It's just a part of a functional group. You can have polarity other places, like iodine bonding to Cl. Now see, this is where iodine maybe has more protons, so there's more to electronegativity. You have to tell me what your understanding of electronegativity is. But we go with just the basic trend, but see, I don't like just go with trends. You need to understand trends. Why is higher and more to the right? Why is this more electronegative than that? Do you really understand? Okay? Yes, it's higher and to the right, but hopefully you want more into than that. Chlorine's more electronegative, so it pulls. All right? You know what pulling is, right? It is, instead of us being nicely, friendly bonded here, it's like, well, you're going to pull. So you're more electronegative. All right? So that's what it is. The chlorine's pulling these electrons. All right? taking electrons away from this region, leading the iodide to be electrophilic. 1 electrons. Why? Because chlorine's taking them. Because it's electronegative. Okay, these are just diatomics. What if we got more than just 2 atoms? By the way, what's a dipole here? Which halogen's partial plus? Yeah. Same. Water. Okay. Now, with just 2 atoms, this dipole is the answer for the entire molecule. When you have more than 2 atoms, you have multiple dipoles, and you have to add those up to get a summation, or a vector summation. Here we have a dipole between the H and O. The oxygen's pulling, this one's pulling. The question is water polar or not? You can't see these individual dipoles. You can only see or observe the net summation. What we need to ask is, do these vectors cancel or not? Why not?
Because there's a lone pair on the oxygen, it's not exactly linear, it's actually shaped.
Right, you got to know the right geometry. The oxygen is really tetrahedral, right? Got lone pair. This is 109.5, tetrahedral arrangement. By the way, I don't do any electron geometry or bent. Bent, that's a what? I would never call this bent. That's electron, not an electron, but a molecular. Yeah, I don't do that. I don't see how you can ignore lone pairs. I will never call this anything other than tetrahedral. That tells you that this bond angle is 109.5, and thus if you want to call it bent, I reckon it is bent, 109.5. But okay. So it's not linear like that. And thus if we have these here, do those vectors, are they equal? Yes, they're equal in terms of intensity, but do they have opposite directions and canceling out? No, they actually add up and you get a net vector summation. Maybe you do some of that in physics. So overall, there is a dipole there. Overall, water is polar. And this is what you can actually measure. The net can be measured in a variety of ways because it leads to other things, consequences. For example, if you put water in an electric field, it will orient itself in a certain way because it's polar. Where a nonpolar molecule won't do anything. It won't respond. Like methyl bromide here, bromine pooling. Carbon is just partial positive. That's a partial positive character. Now, CH bond is considered nonpolar. There is a difference in electronegativity, but it's so small we never consider it. CH, disregard, nonpolar. But you do have the C-Br bond there, which makes the carbon partial positive. Again, that'll be very important for determining reactivity. It's not a formal positive charge. It's a partial positive that comes from polarities. Okay, so we have some down here, need to be able to do. Need to start with structure, Lewis structure, and then assess the individual polarities, and then think about the vector summation. Do they cancel or not? And maybe what's the direction of the net dipole moment, molecular dipole moment, that it's called. Please do those, okay? And we'll see how you did tomorrow. See if there's any questions here. Ultimately, are these polar molecules or not? See some of you this afternoon? Upstairs, check